Okay, so for the first one here, r equals 8 over 2 plus 2 sine theta. The key to this obviously it's in polar form, labeled it in polar form. But the key to these polar forms of conic sections is this first term here in the denominator. We need to make it into a 1. So to do that, we're going to divide both the numerator and the denominator by that value of 2. So r equals, on top, 8 just becomes a 4. 8 divided by 2 is 4. On bottom, we have two different terms to divide. So 2 divided by 2 is 1, plus 2 sine theta divided by 2 is just sine theta. So there are some important pieces of information we have here. One is, this is really a 1 times the sine theta. So E, or eccentricity, is a 1. The eccentricity of a 1 means that this is a parabola. Another piece of important information we can draw out of this. This top here is EP, or E rho, depending on how you want to pronounce it, is equal to 4. Since we know that E equals 1, that means 1 times P equals 4. So P equals 4. Remember, P is the distance from the focus to the directrix. Other important information we get out of here. The fact that this is sine means that our transverse axis is vertical. So for a parabola, that means it either opens up or opens down. And the final piece of information we get out of this is right there, that plus. That means that the directrix is on the positive side of the focus. So the focus in these polar equations, at least the ones we have looked at, the focus is always at the vertex or the origin of our graph. The directrix being on the positive side means the directrix is up above it. And P equals 4 means the directrix is 4 units above the focus. So 1, 2, 3, 4, there's our directrix right there. Now from that and the eccentricity equal 1 means that every point on this graph is the same distance from the directrix as it is from the focus. So that means that the point here on the axis is exactly between the focus and the directrix, 2 units away from each. It's the same distance. If we move this way on the axis next to the focus, we know that every point on that axis is 4 units from the directrix. So we have to go 4 units to each side of the focus to get a point on that parabola. And there we have the basics of our parabola. Those would be the only 3 points I would require you to have on a graph to graph that. So there it is. Now, what if we wanted to express this in standard notation? Well, if I wanted to express this in standard notation, some things that we know about our parabolas. First of all, we know the location of our vertex there is at 0, 2. So what that means is we have x minus 0 squared and y minus 2. The only other piece of information we have is this a term here to figure out what that has to be. That would be basically our slope of this. Well, we have other points here. We have this point here, which is basically 4, 0. So if x is 4, y is 0. And we can use that to figure out what that a term has to be. 0 minus 2 is a negative 2. 4 squared is 16. Well, a times 16 has to equal negative 2. So I need to solve for a, thank you, by dividing by 16. Dividing by 16 here, negative 2 divided by 16 is a negative 1/8 equals a. So that's telling us our equation here is y minus 2 equals negative 1/8 times x minus 0, or just x, squared. There's our standard form of the equation for that parabola. I didn't ask for that as that question, by the way. I just wanted to show you how to do that. Number 2, if I want to graph this, the first thing I have to do is I have to recognize what shape this is. Well, if it were a circle or an ellipse, it would involve sine for one of the variables and cosine for the other. This is a circle or ellipse, obviously. If it was a hyperbola, it would involve secant for one of the variables and tangent for the other. This is sine and cosine, so obviously it's not a hyperbola. If it were a parabola, it would just involve t squared in one of them or t in the other. Technically, instead of theta, I probably should have wrote t in here. Would have made more sense for the parametric equation. So it would have been t, y equals t squared and x equals t, or some variation thereof. So we have sine and cosine here. That's telling us this is either a circle or an ellipse. The number multiplying cosine and sine is different, so that tells us that this is an ellipse. So once we know that this is an ellipse, the parameters in these parametric equations give us the same information we got from our standard equations. The center, the x-coordinate of the center, is at 3. The y-coordinate of the center is at 1. So there is the center of our ellipse. This value here gives us the semi-axis, the horizontal semi-axis. So that means we go 5 each direction from that center horizontally. This is the vertical semi-axis. So that says we go 3 up and 3 down. There is our ellipse. Now we could actually write the standard form of this ellipse from that graph. We know that this is going to be x minus 3 squared and y minus 1 squared just from the coordinates of the center. It's an ellipse, so we know it's going to be plus here, and it's going to equal 1. The semi-horizontal axis is 5, so 5 squared is 25, goes under the x. The vertical semi-axis was 3, so 3 squared is 9, that goes under the y. There is the equation of that ellipse. Now we could come up with that in algebraically rather than looking at the graph if we liked. We have, let me rewrite these equations. X equals 3 plus 5 cosine theta, or cosine t, and y equals 1 plus 3 sine t. So, what I can do is I can solve this for cosine t. So I'd subtract 3. X minus 3 equals 5 cosine t. And divide by 5. So I got x minus 3 over 5 equals cosine t. And I can solve this one for sine t. So I subtract 1. So y minus 1 equals 3 times sine t. And divide by 3 there. To get y minus 1 over 3 equals sine t. And in order to turn this into a standard equation, I want cosine squared and sine squared. So I'm going to square each side of this, and I will square each side of this. Well, for this one over here, x plus 3 or x minus 3 squared, we're just going to write as x minus 3 squared. The 5 squared will square to get 25. That is the cosine squared of t, plus sine squared of t is going to be y minus 1 squared. We're just going to write as y minus 1 squared. 3 squared we're going to write as 9. So this is cosine squared of t plus sine squared of t. And remember, cosine squared plus sine squared always equals 1. So that also gives us that standard form of that equation, just like what we wrote up here from the graph. So from the parametric form, if you can get the graph, there are several ways to convert it back into the standard form. Okay. Anybody have any questions on the parametric equations or polar equations or any of the homework from Monday? Okay. So let's take a look at our new material for today. We're shifting gears here for our last few lectures. And today we're going to talk about sequences. A sequence is just a special type of function. We talked about functions before. Remember, it was f of x equals some expression, maybe 3x squared minus 7x plus 1 or whatever. We had those functions. Well, a sequence is a special type of function. And in a sequence, the domain is simply our whole numbers. So it goes from 1 to some value n, or in most cases, if it's an infinite sequence, it goes from 1 to positive infinity. So this is called a finite sequence. Finite because it has a set number of values, and this is an infinite sequence, because it keeps going on forever. It goes on infinitely. And then the range of the function is just the values of the sequence. So sequences can be defined in a lot of different ways. The most way is using something called a general term. And the general term defines the value of that term of the sequence in terms of its position within the sequence. So an, that is just saying basically f of n, that's the nth value for x equals n, the domain equals n. What is the range value? An is the range value for the domain value of n. Where the formula, let's say it's given as 2n over n plus 2. So that's saying that the nth term has a value of 2n over n plus 2. So let's say we are asked to find the first 5 terms of that sequence. So we start off with n equals 1. A1 is going to be 2 times 1 over 1 plus 2. That is 2/3. For n equals 2, A2 is going to equal 2 times n becomes 2 times 2 over n plus 2 becomes 2 plus 2, which is 4 over 4, or just 1. N equals 3. A3 is 2 times 3 over 3 plus 2. Well, 2 times 3 is 6, 3 plus 2 is 5, so that's 6/5. Notice I leave it as 6/5 because often leaving it as an improper fraction like that makes it easier to see the pattern in the sequence. For n equals 4, A4 will be 2 times 4 over 4 plus 2. That's 8 over 6. We will reduce that to 4/3. And n equals 5, that's our fifth term, so that's the last one we need to find. A5 equals 2 times 5 over 5 plus 2. So that's 10 over 7. So 10/7. So we would express this answer, the first 5 terms, as 2/3, comma 1, comma 6/5, comma 4/3, comma 10/7. That is the first 5 terms of that sequence. What if I ask you to find the 21st term? Well, because we have a general term, that means we're simply finding A21. So we put 21 in for n, so 2n becomes 2 times 21. n plus 2 becomes 21 plus 2. That is simply 42 over 43. Or sorry, 42 over 23 for that term. Or 1 and 19/23 if you do want to make it into a mixed number. So in your notes, I'm going to give you another example. So our general term here, an, equals 2n squared minus 3. And I want you, 1, find the first 4 terms. We'll only do 4 instead of 5. And 2, find the 15th term. So I'll give you a couple. So for n equals 1, we have a1 is equal to 2 times 1 squared minus 3. Well, 1 squared is 1, times 2 is 2, minus 3 is negative 1. So our first term of the sequence is negative 1. For n equals 2, a2 is 2 times 2 squared minus 3. 2 squared is 4, times 2 is 8, minus 3 is 5. So our second term is 5. For n equals 3, a3 is 2 times 3 squared minus 3. 3 squared is 9, times 2 is 18, minus 3 is 15. So the third term is 15. And for n equals 4, a4 is 2 times 4 squared minus 3. 4 squared is 16, times 2 is 32, minus 3 is 29, is the fourth term. So that's the first 4 terms of that series. The 15th term, for n equals 15, well, a15 is going to be 2 times 15 squared minus 3. Going to have to write this one out. 15 squared is 225. 2 times 225 is 450. Minus 3 is 447. So the 15th term is 447. Notice those terms get large quickly. That's because there's a power on that index of the sequence on the end, so that makes that get larger rather quickly. Another way we can express a sequence, rather than using a general term, which is what we did up above, is we can use a recursive formula. And what the recursive formula does, it defines a value of a term from the value of previous terms. So the value or values of previous terms. So in most cases, most people think of recursive formulas as simply using the previous term, one previous term. You know, an example of that might be an is equal to 2 an minus 1 plus 3, like that. So in order to find, so let's say we're given if a6 equals 11, find a7, the seventh term in that sequence. So to find a7, it's going to be 2 times a6, n minus 1 would be a6, so that's going to be 2 times 11 plus 3. Well, 2 times 11 is 22, plus 3 is 25. So a7 equals 25. Well, let's say for the same one we are asked to find a9. Assuming that a6 is 11. Well, we've already found a7 is 25, so our next step would be to find a8. a8 is going to be 2 times a7, so 2 times 25 plus 3. Well, 2 times 25 is 50, plus 3 is 53. So then we'll do the next step to get to a9. It'll be 2 times a8, so 2 times 53 plus 3. Well, 2 times 53 is 106, plus 3 is 109. One of the powers of a recursive formula. Well, let's start this way. One of the weaknesses of the recursive formula is not only do we have to have the formula, but we had to be given a starting point. Not necessarily a1, but we were told here that a6 had that value of 11. So the recursive formula itself is no good to us unless we know one of the points of the formula. The strength of a recursive formula is that recursive formula can generate an infinite number of different series based on what the starting point is. Is this formula here, an equals 2 an minus 1 plus 3, is a totally different series if I give you a1 equals 7 compared to if I give you a1 equals negative 2. So by changing the starting point, the value of the starting point, I can totally change the series. That's one of the strengths of that recursive formula. Now, we were given this formula. I'm going to ignore this for a minute and go back to that original up there. an equals 2 times an minus 1 plus 3. And I gave you that a6 equaled, that was 11, right? Yep, 11. What if I ask you from that to find a5? Well, I can substitute into this formula, but now A6 is the larger, the further term, the bigger index. So that has to go for AN of 11 equals 2 times AN minus 1. Well, 6 minus 1 is 5. So A5 would be there. So I'm using that recursive formula backwards to back up a step in my sequence. So I can subtract 3 to get 8 equals 2A5. And I'll divide by the 2 to get A5 by itself to get 4 equals A5. So we were able to work backwards in the sequence to find previous terms from the one we are given. Well, not all recursive formulas use just a single term. Some recursive formulas use several previous terms. An example of that is called the Fibonacci sequence. The Fibonacci sequence is a recursive sequence where A1 is given to be 1 and A2 is given to be 1 and AN is defined to be AN minus 2 plus AN minus 1. What does that mean? Well, we have the first two terms in the series here, A1 and A2 is 1 and 1. A3 is going to be A1 plus A2, so 1 plus 1. The third term is a 2. A4 is going to be A2 plus A3. Well, A2 was 1, A3 was 2, so that's going to be a 3. But A5 was going to be A3 plus A4. Well, A3 was 2 and A4 is 3. That gives us a 5. And I could actually do it right in the sequence quicker. 3 plus 5 is going to be 8. 5 plus 8 is 13. 8 plus 13 is 21, and I could keep going from there. That is the first 8 terms of that Fibonacci sequence. Now, this is officially the Fibonacci sequence. Must have A1 is 1 and A2 is 1. But there are different variations used on that where we define those initial terms differently. But it's still found that the next term is found by adding together the previous two. There are actually a lot of examples in nature where that holds true. Now, as we're talking about our sequences, we need to define another operation. And this is one that many of you have probably seen before. But this operation is a factorial. It is denoted with an exclamation point. What it means, n factorial, means that it's n times n minus 1 times n minus 2 all the way down to times 1. So what does that mean? Let's say I have 4 factorial. That means I am starting at 4, doing 4 times 3 times 2 times 1. 4 times 3 is 12, times 2 is 24, times 1 is 24. So 4 factorial is 24. Now, some rules of our factorial, or properties of our factorials, I should state, that make them easier to work with. 5 factorial, I could start by doing 5 times 4 times 3 times 2 times 1 if I wanted to, and I could calculate that out. Or I could realize that, hey, if I start right here, that's just 4 factorial. So 5 factorial is equivalent to 5 times 4 factorial. And since I already know the 4 factorial, That's just 5 times 24, or 120. So I don't have to go ahead and multiply all that out, starting at 5 working down. So let's say I have 7 factorial. Instead of doing 7 times 6 times 5 times 4 times 3 times 2 times 1, since I already know that 5 factorial is 120, I can replace that. And I can just do 7 factorial as 7 times 6 times 120. Giving us 5,040 is 7 factorial. The next property of factorials that we want to talk about is, let's do dividing factorials. 5 factorial divided by 3 factorial. Well, 5 factorial is just 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. What we notice is those terms just divide out of our fraction. So we're left with simply 5 times 4. This is 20. So that gives us a generic term. If I have n factorial over m factorial, that's just going to be n times n minus 1 all the way down to n minus, got to be careful how I word this, I should say all the way down to m plus 1. So I don't have to worry about those bottom m terms because they divide out in the factorial. The reason we bring up factorial notation here is factorials are often used to define the generic term of many of our sequences. We might have a sequence that is defined as an is equal to n factorial over n to the third power. So let's find the first 4 terms. Well, a1 is going to be 1 factorial over 1 to the third power. Well, 1 factorial is defined to be 1. 1 to the third power is just 1. So a1 here is just 1. a2. Well, that's 2 factorial over 2 to the third power. 2 factorial is 2 times 1, which is just 2. 2 to the third power is just 8. So that is just 1/4. So the second term is 1/4. a3, well, that's 3 factorial over 3 to the third power. 3 factorial is 3 times 2 times 1, which is 6. 3 to the third power is 27. So 6 over 27, or 2/9. And finally, let's do a4. That is 4 factorial over 4 to the third. Four factorial is just 4 times 6, or 3 factorial. So 3 factorial is 6, so 4 times 6 is 24. 4 to the third power is 64. Both of those divide by 4. Is there anything bigger? They both divide by 8, actually, to give us 3/8. So those are the first 4 terms of that sequence. 1, 1/4, 2/9, and 3/8. Of course, it will continue. So in your notes, I want you to write for an equals 5n over n minus 1 factorial. I want you to find the first 4 terms. Now, before you do that, I need to define something for you. Because in the first term, you're going to end up with 0 factorial. 0 factorial is defined to be 1. So 1 factorial is also 1, so that can be a little bit confusing, but 0 factorial is defined to be 1 so that formulas like this will work. So I'll give you a minute here to find those first 4 terms. Some of you aren't finished yet, but that's okay. Let's go ahead and look at this. A1 is going to be 5 times 1 over 1 minus 1 factorial. Well, 5 times 1 is 5. 1 minus 1 is 0. Well, 0 factorial is 1, so that's 5 over 1, or just 5, is our first term. A2, well, that'll be 5 times 2 over 2 minus 1 factorial. 5 times 2 is 10. 2 minus 1 is 1, and 1 factorial is 1. So it's 10 over 1, or 10 for our second term. A3 will be 5 times 3 over 3 minus 1 factorial. 5 times 3 is 15. 3 minus 1 is 2, so it's 2 factorial. So 15 over 2 factorial is just 2, so that is 15 over 2, or 7.5. We're going to write it as 15 over 2 for our third term. And finally, A4, which will be 5 times 4 over 4 minus 1 factorial. 5 times 4 is 20. 4 minus 1 is 3. 3 factorial, 3 times 2 times 1 is 6. So that's 20 over 6, or 10 thirds, or 3 1/3. Our third term is 10 thirds. And of course, it'll continue from there. But our fourth term is 10 thirds. So those are our first 4 terms. The next notation that we want to talk about with our sequences is something that looks like that. Now, from now on, you're going to see me write it quickly, just like that, without the little tails on it. But it is the summation notation. And what it is doing is it's telling us to add together a certain number of terms. So, for example, it might tell us to add together from I equals 1 to 4 I plus 1 factorial over 2i. What that is telling me to do is this is saying I is my index of A. So it is saying find A1, A1, A2, A3, and A4, and add them together, where this is the general term for A. So, if I is 1, 1 plus 1 factorial over 2 times 1, well, that's just going to be 2 over 2, which is 1. So, A1 is 1. So that was for I equals 1. For I equals 2, we have 2 plus 1 factorial over 2 times 2. Well, 2 plus 1 is 3. 3 factorial is 6. 2 times 2 is 4. So that's 3 halves is what that reduces to. So A2 is 3 over 2. A3 for I equals 3. That'll be 3 plus 1 factorial over 2 times 3. 3 plus 1 is 4. 4 factorial is 24. 2 times 3 is 6. 24 divided by 6 is 4. So A3 is 4. And finally, for I equals 4. 4 plus 1 factorial over 2 times 4. 4 plus 1 is 5. 5 factorial is 120. 2 times 4 is 8. 120 divided by 8 is 15. So if I add those up, 1 plus 3 halves plus 4 plus 15, I get 21 and a half. So 21 and a half is equal to the summation from I equals 1 to 4 of I plus 1 factorial over 2I. Sometimes it helps to be able to write these backwards. If I give you the terms to try to find the general formula, if I give you the terms of a sequence as, well, let's try to keep this simple on the first one. Let's call it 3, 5, 7, 9, 11, and so on. That is the first 5 terms of my sequence. There are a lot of different ways I could define this. I could define this as 1 plus 2n equals my generic term. Or I could define it as an is equal to 3 plus 2 times n minus 1. Notice all I've done there is I've shifted it 2 spots. If I distribute this 2, I got 3 plus 2n minus 2. Combining the 3 and that negative 2 would give me 1. So that's actually the same formula, just a different way of expressing it. So I can shift the starting point. Now this formula is a lot simpler than this one, so I would prefer this one. But this one is not wrong. Well, that was relatively simple. It just went up by a constant value from one step of the sequence to the next. Let's look at one a little bit more complex. Let's say we've got 1/3, 2/4, 3/5, and 4/6, and so on. So here, if we look at it, we notice that both the numerator and the denominator go up by 1 each time. So if I define n equals 1, 2, 3, and so on, an here is just n over, this would be n plus 2 as my general term. Well, let's look at something a bit more complex. 1 over 9, 2 over 9 squared, 3 over 9 to the third, 4 over 9 to the fourth, and so on. So our general term here, an, if I define n equals 1, 2, 3, 4, that's simply n over 9 to the power of n as our general term. So the big key here is you have to be able to look for patterns. Now when I wrote these out, I just wrote them as a sequence. But I could write them as a summation. I might write 6 plus 9 plus 12 plus 15 plus 18 and so on. Since it's plus in there, it's not just a series, it is a summation. But the first step is still going to be to find the general term. My general term here, an, the simplest way to write that would be 3 plus 3n. If n is 1, it's 3 plus 3 is 6. If n is 2, 3 times 2 is 6, plus 3 is 9, and so on. So then this summation becomes the summation from I equals 1 up to, this would be 1, 2, 3, 4, 5, of 3 plus 3i. Notice I put I in where the n was for our general term. Okay, for right now it is break time, so let's go ahead and take a break. We'll come back at 10:30 and we'll start talking about specific special types of sequence. Next step is we want to talk about a couple of special types of sequences. The first type of sequence that we want to talk about is called an arithmetic sequence. And an arithmetic sequence has two properties. It has a first, the main property is that after the first term, each term goes up or increases by a constant amount. So what we have is we have a first term which we define as A1, and we have what's called a common difference. That is that constant increase, which we're going to just refer to as D for difference. So if I know the first term in that constant difference, or common difference, let's say I know that A1 equals 7 and D equals 4. Well, I know the first term of my sequence is 7, and every term after that has a difference of 4, or goes up by 4. So 7 plus 4 is 11. 11 plus 4 is 15. 15 plus 4 is 19. 19 plus 4 is 23. And it continues. We can express an arithmetic sequence in terms of A1 and D in a couple of different ways. We can express the general term of an arithmetic sequence as AN equals A1 plus n minus 1 times D. Now we saw up above there was a way to adjust that. So we could alternatively write this as AN equals A1 minus D plus n times D. Both of those are equivalent formulas. Notice if I just distribute the D here, I get ND minus D. Well, that's moving that minus D with the A1. The recursive term, recursive formula, is simply AN equals AN minus 1 plus D. That's just the definition of the arithmetic sequence, is you take a previous term and you add that constant difference to it. So let's look at some examples using that here. Let's say if A1 equals 3 and D equals 5. Find the first 5 terms. Well, our first term is 3. A1 is 3. After that, each term goes up by 5. So 3 plus 5 is 8. That's the second term. 8 plus 5 is 13. That's our third term. 13 plus 5 is 18. There's our fourth term. And 18 plus 5 is 23. There's our fifth term. There's the first 5 terms. Alternatively, we might be given that A17 equals 49 and D equals 3. We might be asked to find A13. Well, we got A17 here equals 49. We need to work backwards to A16, A15, A14, and A13 with that common difference of 3. So going backwards, of course, we're going to go down by 3. So A16 would be 46. A15 would be 43, A14 would be 40, and A13 would be 37. So A13 is 37. Well, that's all fine as long as we have relatively small numbers for the index of our term. But what if I give you something like this? A57 equals 219, and D equals 7. Find A12. I am not about to start out at A57 equals 219 and work my way backwards to A12. That's just too many steps. That's 45 steps. Not going to do it. But what we can do is this. We know that the general term, depending on which form we want to write it, AN equals A1 plus n minus 1 times D. Well, we know that A57 is 219. So that's going to be A1 plus n is 57 minus 1 times that common difference that was given as 7. And now we can solve to find A1. So I've got 219 equals, the A1 isn't going to change. 57 minus 1 becomes 56. Well, 56 times 7 is 392. So 219 equals A1 plus 392. And now we subtract the 392 to get A1. So 219 minus 392 is going to be a negative 173. So A1 equals a negative 173. So what that tells us is our general formula is actually AN equals a negative 173 plus n minus 1 times 7. So when we are asked to find A12, we can use this formula. A12 is going to be a negative 173 plus 12 minus 1 times 7. So the negative 173 doesn't change. 12 minus 1 is 11, so 11 times 7. So negative 173, 11 times 7 is 77, equals negative 96. So A12 is a negative 96. Now, all the examples I've given so far, the common difference has been positive. It doesn't necessarily have to be. Let's say I give you that A27 is 238 and A32 is 218. I want to find A1, D, and the formula for AN, the general formula for AN. Well, I know A27, which is 238, equals A1 plus 27 minus 1 times D. I also know that A32 here, which is 218, equals A1 plus 32 minus 1 times D. Comparing these formulas, there are a lot of things I can do with them. One of the things I would do with them is I would subtract them. You could subtract this formula from this one. It would cancel out the A1s and it would give you a formula for D. Well, let's take a peek at this. First thing I want to do before I do that, though, is I want to reduce this term in each of them. So this one, the 238, isn't going to change. A1 isn't going to change. But 27 minus 1 is going to be 26D. So I'll do the same over here. The 218 isn't going to change. And the A1 isn't going to change. But I'm going to do 32 minus 1 is 31D. Now it doesn't matter which order I subtract here. So I'm just going to take this one minus this one. So I have 238 equals A1 plus 26D. On the left side, I'm going to subtract the 218. On the right side, I'm going to subtract the A1 and 31D. Now to make this simpler, here's what I'm going to do. I'm going to take this whole equation here. 218 equals A1 plus 31D. I'm going to erase some of my mess here quick. And I'm going to multiply that whole equation by negative 1. It gives me a negative 218 equals negative 1 A1 minus 31D. And now what I'm going to do is I'm going to do this just like we did elimination in our systems of equations, because that's what this is. This is just a system of equations. I have a negative 1 A1. So negative 218 equals negative 1 A1 minus a 31D. So on the left side here, 238 plus a negative 218 is just 20. A1 and negative A1 cancel out. 26D and a negative 31D is a negative 5D. So I go ahead and I solve for D by dividing by a negative 5, giving me negative 4 equals D. Now that I know that D equals negative 4, we can go back and find A. Remember we had, and it doesn't matter which one we use, 238 equals A1. This was for the A27, by the way. Plus 27 minus 1 times D is negative 4. We can now solve that for A1. 238 equals A1 plus 27 minus 1 is 26 times negative 4. 238 still doesn't change, equals A1 plus 26 times a negative 4 is a negative 104. To solve that for A1, then, we're going to add 104 to get rid of the negative 104, giving us 342 equals A1. So now we have got two of the pieces we were asked to find. A1 is 342. D, or common difference, is a negative 4. The AN formula, well, AN equals A1 of 342 plus N minus 1 times D of negative 4. So there's our formula. Let's take some time to talk about sums of an arithmetic sequence. Now we cannot talk, there's finite sums and there are infinite sums. A finite sum is just that, it's for a set number of terms that get added together. We can always do a finite sum of any sequence, being more or less work, but we can always do it. Infinite sums, however, cannot be done with arithmetic sequences. In order to do an infinite sum, a sequence must be what we refer to as a converging sequence. We're not going to talk too much about converging sequences in this course, but if you go on to calculus, that is a term that comes up a lot. It's converging versus non-converging sequences. And how do you prove it? So for arithmetic sequences, the finite sum, infinite sum, if we added an infinite number of terms together, it's always going to either blow up to a positive infinity or negative infinity. So we're going to stay away from that, and we're going to work strictly with finite sums. So the finite sum for an arithmetic sequence for I equals 1 to n, where n is a finite number, an integer, or sorry, a whole number, I should say, is equal to n over 2 times a1 plus an. So let's do this. Let's say I want to do the finite sum from I equals 1 to 20 of the arithmetic sequence 7 plus let's do 7 plus I minus 1 times 3. First of all, this is just the general term. It's saying that A1 equals 7 and D equals 3. So I have right over there, I have A1 is just 7. I need to find, since we're going from 1 to 20, I need to find A20. So A20 is going to be just 7 plus 20 minus 1 times 3. So that'd be 7 plus 19 times 3, or 7 plus 57, which is 64. So A20 is 64. So the finite sum from I equals 1 to 20 of that arithmetic sequence is n is 20 over 2 times a1 is 7 plus a20 is 64. So now there's a couple of different pieces I can do separately here. First of all, 20 divided by 2 is 10, and 7 plus 64 is 71. 10 times 71 is 710. If you wanted to actually go ahead and figure that out, find all 20 of those terms and add them up, it would add up to 710. So in your notes, I would like you to find for me quick the finite sum from I equals 1 to 10 of 3 plus I minus 1 times 7. I'll give you a minute or so to work that out. First of all, A1 is just going to be the 3. N equals 10, so A10 is going to be 3 plus 10 minus 1 times 7. So that'll be 3 plus 9 times 7, which will be 3 plus 9 times 7 is 63, which will give us 66. So the formula for this, n is 10 over 2 times a1 of 3 plus a10 of 66. 10 over 2 is 5. 3 plus 66 is 69. So that is 345 is what that multiplies out to be. So that is the sum. Any questions on finding that finite sum of that arithmetic sequence? Okay. So a slightly more powerful sequence is a geometric sequence. A geometric sequence has the property that after the first term again, each term goes up by a constant multiplier. Goes up or down, really, by a constant multiplier. So a geometric sequence is defined by that first term. Once again, that's A1. And instead of a common difference, it has a common ratio. Because it's not just a number added to the terms, it's multiplied. So it's not the difference between the terms isn't the same, but the ratio from one term to the next is the same. So we call that common ratio R. So if A1 is 3 and R equals 2, if I'm asked to find the first 5 terms, well, the first term is just A1, that's 3. Times 2 would be 6, that's the second term. 6 times 2 would be 12, that's the third term. 12 times 2 is 24, that's the fourth term. 24 times 2 is 48, that's the fifth term. And they would keep going up from there. Our formula for the general term AN, again, it starts with A1 times r to the power of n minus 1. So instead of adding n minus 1 times our common difference like we did with the arithmetic sequence, with the geometric sequence, we're multiplying by that ratio to the power of n minus 1. So for our example up above, a1 equals 3 and r equals 2, let's say we're asked to find the 15th, let's keep this more reasonable. Let's find the 11th term. Well, our 11th term here, a11, is going to be a1 of 3 times r of 2 to the power of 11 minus 1. Well, 11 minus 1 is 10. 2 to the power of 10 is 1,024. And 3 times 1,024 will be 3,072. So the 11th term is 3,072. The recursive formula is simply an is equal to a n minus 1 times r, times that constant ratio, common ratio. Well, when we are dealing with these geometric sequences, the sums become much more vital. And when we have a geometric sequence, it is possible to have what's called a converging sequence. And this isn't really a term that our textbook uses much, but what it is if r is between -1 and +1, the sequence will converge. And in that case, we can have an infinite sum. In that infinite sum, the sum from I equals 1 to infinity is simply going to equal, for the AI, it's simply going to equal our first term a1 over 1 minus r. Well, let's take a look at that. Let's say we have a first term of 8 and a common ratio of 1/2. So our first several terms would be 8. 8 times 1/2 would be 4. 4 times 1/2 would be 2. 2 times 1/2 would be 1. 1 times 1/2 would be 1/2. 1/2 times 1/2 would be 1/4. 1/4 times 1/2 would be 1/8, and it would keep going. It's smaller and smaller and smaller. It's going to converge towards 0. Never touch 0, but it's going to converge on 0. It's asymptotic, has an asymptote. That's one of the qualifications for convergence. To find the infinite sum now, from I equals 1 to infinity, for that, we're going to take a1, which is 8, over 1 minus r, so 1 minus 1/2. So that'll be 8 over 1 minus 1/2 is 1/2. 8 divided by 1/2 is 16. If we were to start adding these terms together, we would find as we keep going, they will get closer and closer to 16. If I just put it right here, 8 plus 4 is 12, plus 2 is 14, plus 1 is 15, plus 1/2 is 15 1/2, plus 1/4 is 15 3/4, plus an eighth is 15 and 7/8, you can see that total is getting closer and closer to 16. If we go out to infinity, if we go on forever, that total converges on 16. So that is the sum of that infinite series. The finite sums are slightly more complex. Now the finite sums work for any values of r, but we do typically focus on the r being between -1 and +1. So let's say the finite sum for I equals 1 to n for ai in this sequence is equal to a1 times 1 minus r to the power of n divided by 1 minus r. So let's say we want to do a finite sum from I equals 1, let's go to 10, for an infinite series where a1 equals 8 and r equals 1/2. So it's the same infinite series we had up above, but we're instead of doing 1 to infinity, we're only doing 1 to 10. So a1 is 8. This is going to be 1 minus 1/2 to the power of 10 over 1 minus 1/2. So on top, this is 8 times, well, let's just punch this in the calculator. The easiest way to do that is we're going to put this bottom in parentheses. So we punch this in the calculator. It's going to be 8 times parentheses 1 minus, I'm going to do a parentheses here, 1 divided by 1/2, close parentheses, the power of 10. Arrow to make sure I'm out of the power. Close the parentheses on the numerator. Then I'm going to divide by the denominator. So I'm going to put the denominator in parentheses, 1 minus 1/2, and close the parentheses on the denominator. We get 15.984375. Now, if you look at that, I believe that ends up being like, oh, what would that be? Oh, I think that comes out to be 15 and 63/64 or something like that, if you were to change that into a fraction. But that is the finite sum of those first 10 terms. Now, applications of each of these. The application of a finite sum of a geometric series. One of the biggest ones is an annuity. An annuity is where you pay in a certain amount each term. Now, unfortunately, in this annuity, we start out with an amount P, and then the next term we have that amount P plus times its interest. Well, its interest is 1 plus its rate. So the next term is going to be P plus 1 plus the interest earned. The next term is going to be P times 1 plus the interest earned squared, which is going to have sat there for 2 years, or 2 terms, and so on. Well, if R is the annual interest, and it compounds more often than just annually, we have to adjust that rate. and the formula, and you'll be able to see the similarities from the annuity, the finite sum formula here. The total, the amount in that annuity is equal to P, which is your payment amount, times, in parentheses, 1 plus R divided by N. That is just adjusting your rate for the number of compounded periods in a year. So if it's compounded monthly, N is 12. Compounded quarterly, so monthly, N equals 12. Quarterly, N equals 4. Annually, N would equal 1, and so on. To the power of N times T, where T is your number of years. That's just what each term is there. Minus 1 over R divided by N. That's our rate. Now this is derived from that formula, but we're looking at, we've kind of altered the formula based on R and N, so the minus 1 is moved up top. If we had more time, I'd go through the algebra to show how we got from one to the other. At this point, we're just going to leave that formula out there. And I'm going to show you an example of, if you invest $50 a month at 8% for 20 years. Now, most of you are pretty young, so investing, you've got way more than 20 years ahead of you for retirement. But let's just take a look at what would happen if you did $50 a month at 8%. So that's going to be 50 times, we do have to have two sets of parentheses here. 1 plus 8% is going to be written as 0.08. It's per month. That's $50 a month, so this is going to be compounded monthly, so divided by 12. To the power of 12, because it's monthly, times 20 years, minus 1, we'll close the parentheses there. Then this is going to be divided by that 0.08 over 12. So let's punch this in. 50 times, we have to have the two open parentheses, 1 plus 0.08 divided by 12. Close the parentheses to the power of 12 times 20. Arrow out of the power, minus 1. We close that parentheses again, divided by. Now the denominator has to go in parentheses when we put it in the calculator. So parentheses around 0.08 divided by 12 and close that parentheses. We get that after 20 years, at just $50 a month, you have $29,451. If we doubled that to be $100 a month, we would double this total to be almost $60,000. If we take it for, most of you are in your 20s, you're going to be in your 60s when you retire. If we took that to be 40 years instead, so all that's going to change in this formula is this is going to be 12 times 40 instead of 12 times 20. That goes up drastically. That $50 a month is almost $175,000 in your 60s. Just on my soapbox for a second, getting you to think about retirement savings. An application of a finite sum, moving back to, I just lost it now. I just lost my train of thought. Oh, sorry, a finite or an infinite sum for these geometric series would be a repeating decimal. Let's say I have 0.272727. I can think of this as being and that repeats. I can think of this as being a geometric series. The first term is 0.27. The second term is 0.0027. The third term is 0.000027, and so on. So A1 is 0.27. And R, my common ratio, it's being multiplied each time by 1/100th, or 0.01, moving the decimal point over 2 spots each time. So the infinite series here, the sum of that infinite series, would be A1, 0.27, over 1 minus R of 0.01. 0.27 isn't going to change. 1 minus 0.01 is 0.99. To reduce that fraction, first of all, to get rid of the decimals, there's 2 decimal places in both the numerator and denominator. I'll multiply by 100. Moves the decimal point over 2 spots. I have 27 over 99. Now I can divide by 3, because both of those reduce by 3. Actually, I can divide by 9, because both of them divide by 9, to give me 3/11ths. That fraction, 3/11ths, is 0.2727. 3 divided by 11 is 0.27272727. Okay, so we have homework from Monday that is due tomorrow. We have new homework from today that'll be due Wednesday. That'll be due on Thursday, is tomorrow. New homework from today, which will be due next Tuesday. And there is a quiz on that old material that's going to be due this Friday. Anybody have any questions? Okay, we are in the stretch run here now. We have 3 more lectures left before the final test. Only 2 of them are on original material. That final lecture is a review for the test, just to give you an idea of what to make sure you study for the test. And then, of course, coming up December 18th is our final test. So make sure you're preparing for that. There is a study sheet out there, or a study item out there in my math lab that you can use to start studying for that final test if you would like. Once again, that is extra credit if you complete that. Well, you guys have a great week, and we'll see you all on Monday.